All right, guys, so let's take a look at this page 714, 79, and 97 odd. So I've had requests to do questions 83, 97, and I believe someone asked me to do, let me take a look here, 87. Would you agree with that? Okay, so they asked me 83, 87, 97. Rachel, did you have some other ones that you... 89. Okay, let's see what we can do with this stuff. I'm not making any promises. Okay. All right, let's start with 83. I think I can do C. Could you do A and B? All right, C was an issue. All right. So question 83C tells me that you have a mixture with 0.10 molar sodium nitrite, and to that you're mixing 0.20 molar calcium nitrite. Alright? Okay, so let's take a look. When you take sodium nitrite, and basically you've got two salts here, correct? When you take sodium nitrite and you place some water, what happens to that sodium nitrite? What happens to it? It dissociates, right, into sodium ions and nitrite. Do sodium ions have an effect on pH? Those are cations that you would find in a strong base, correct? Do they have an effect on pH? The answer is no. What about nitrite? Does that have an effect on pH? Yep. Is this not an anion that you would find in HNO2? And that happens to be a weak acid? So conjugates of weak acids would be what? Would they be strong or would they be weak? This conjugate is in fact a strong base. So this will have an effect on pH with any of the water molecules that are floating around in that beaker behind in the background. All right? Okay, how about the calcium nitrite? When that falls apart, what do you make? Calcium 2 plus and more nitrite. Again, calcium is a cation that you would typically find in a strong base, so it won't really have an effect on pH. However, the nitrite is a conjugate that is also common to the weak acid HNO2, so it in fact is a strong conjugate base. And one thing that you should notice here is when you write the equation for how CaNO2 dissociates, you really need to put a 2 in front of the NO2, all right, to conserve the number of atoms. Okay, so if it was 0.1 molar NaNO2, right, then what is the concentration of nitrite produced by sodium nitrite in solution? 0.10. Good, same thing. If we had 0.20 molar calcium nitrite and that dissolved, what is the concentration of nitrite that we make over here on the right hand side? 0.4. It's twice as much. You have to take 0.2 multiplied by that coefficient there, it's 0.4. What is the total amount of nitrite in solution here? 0.1 plus 0.4 is 0.5, right? So all I did is I took the nitrite made by the first salt and added it to the nitrite made by the second salt that are mixed together, all right? So essentially what I have is 0.5 molar of nitrite reacting with the water in the background, correct? There's 0.5 of this. What is that nitrite doing to the water in the background? is stealing a hydrogen from it, right? And turning into HNO2. And what else is it leaving behind? Hydroxide. At time 0, how much of these products do I have in that beaker? 0. How much of this nitrite is going to do this? Is it a lot? I don't really know. So what am I going to subtract? X. What's my E line? 0.50 minus X, X, and X. All right. If I were to write a mass action expression for this reaction, right, in order to solve for X, what would that expression be? X squared over 0.50 minus X. What do I set that equal to? Do I set that equal to a Ka value or a Kb value? Kb. Why Kb? Because I'm making hydroxide. Okay? Plus, if I look in Appendix D, I'm not going to have an easy time finding a Ka for NO2 minus. Right? So anytime that you demonstrate hydroxide being formed or an acid being formed, that equilibrium should be described by a Kb value. If you show a hydronium being made or an acid falling apart, that's when you use Ka values. All right, so how do I get Kb? Well, if I look in the back of the book, they're going to give me the Ka for HNO2. All right? The Ka for this is, let me look this up. Is it 4.5 times 10 to the negative fourth? Yeah, 4.5 times 10 to the negative fourth. All right, so how do I get Kb out of Ka? So you remember the formula Ka times Kb equals Kw? So to get Kb, you're going to do Kw divided by Ka. So Kw is 1 times 10 to the negative 14th divided by 4.5 times 10 to the negative 5th. All right, let's do just some quick mental math here, right? What's 10 to the negative 14th divided by 10 to the negative 5th? 10 to the negative 9th. Why do I care? Because just by looking at that estimate, I know whether I can use the 5% rule or not and make my life easy. If this divides out to 10 to the negative 9th, can I use the 5% rule? So using the 5% rule, I'm allowed to do what? I'm allowed to ignore the x in the denominator, which makes my math a lot simpler, right? Okay, so if I ignore the x in the denominator, I would basically divide this, multiply by 0.5, take the square root of it, and so then x should be 3.3 times 10 to the negative 6th. All right? What did the question ask for? They wanted the hydroxide concentration. All right, let me zoom back so you can see. What does X tell me? The hydroxide concentration. All right. Then they go and they ask, well, what's the pH? Well, can I get pH out of hydroxide? Not directly. What could you get out of hydroxide? The pOH. So what's the pOH of this sucker? The pOH is the negative log of 3.3 times 10 to the negative 6. So it's going to be like 5 point something. As a matter of fact, it's exactly 5.48. Is it off screen? A little bit? It's like 5.48. Okay? All right, but they didn't want pOH. They really wanted pH. So how do I get pH out of pOH? 14 minus 5.48, which would happen to be 8.52. Are we good? All right, let's take a look at question number 87. Question number 87 tells me that I have 3 salts, NaF, NaCl, NaOCl. And they're telling me that when you take 0.05 mole of the salt and you dissolve in water to form a 0.5 liter solution, the pH of the solution is 8.8 or 8.08. I'm sorry. Which of the salts do they use? We're not going to do any math whatsoever. We're going to do this entirely qualitatively. Okay? All right, so first things first. One of these substances I can completely omit from consideration. Which substance would I get rid of? How about NaCl? If I put some table salt in water, does it change the pH? No. Because the cation is a common ion to a strong base. The anion is the common ion to a strong acid. Neither acid has an effect on pH. So table salt, seawater, has a pH of 7. All right? Okay, so then I got to look at these other two and figure out which one's the more likely candidate. All right? So NaF. What's going to affect the pH? Is it going to be the sodium or the fluorine? The fluorine, not the sodium. The sodium is a common ion to a strong base. So in neither of these cases does the sodium affect pH. It's the other thing that matters. Okay? All right. Is that a terribly basic substance? No, it's really close to 7, right? Okay. So how do you think we're going to figure out whether it's this or that? I'm going to look in Appendix D, and what am I going to look up? I'm going to look at Ka value. So I'm going to look up the Ka value for HF. And I'm going to look up the Ka value for HOCl. All right? And I want you to remember what happens here. I'm going to look them up. All right? So in the back of the book, Appendix D, let's see. So hydrofluoric acid is, I can't tell, 6.8 times 10 to the negative 4th. And then hypochlorous acid is 3.0 times 10 to the negative 8. What would I do with those Kas? Do I really look at the Ka or do I look at the Kb? Are these acids or bases, these conjugates? They're bases. So I really should look at the Kb's, right? And the one that's going to give me the pH closest to 7 is going to be the one with which Kb? The bigger Kb or the smaller Kb? No, the smaller Kb. So what you're trying to figure out is which of these two has a smaller Kb, because a smaller Kb means that it's not as effective of a base, right? It's not as good of a base. Do I really want to calculate this? Do I really want to waste my time calculating? Can't I already tell who's going to have the smaller Kb? Who's going to have the smaller Kb? The guy with the bigger Ka. Most likely that substance is hydrofluoric acid. Okay? All right, let's take a look at the next one. 89, was it? Oh, I don't want to do it. What's wrong with it? Oh, I guess we could do it. All right. 89. Just because I like the region. I don't like anybody else in the room, just you, Rachel. All right, 89. I'm joking. I kid. All right. So you have some sorbic acid. It has this formula C5H7COOH. It's a weak monoprotic acid. So all that means is that's jargon for it only has one hydrogen to give up to the environment. And its Ka is 1.7 times 10 to the negative 5th. It says its salt, which is called potassium sorbate, is added to cheese to inhibit the formation of mold. What is the pH of a solution containing 11.25 grams of potassium sorbate in 1.75 liters of solution? All right, well, so think about what's in the beaker. What's in my beaker? Water and this salt, right? They're not putting the acid in, it's just the salt, okay? All right, so write a reaction between these two substances, right? So what's the formula for potassium sorbate? It's going to be KC5H7COO plus H2O. And in all actuality, no one really cares about the potassium that's in it. The potassium's just spectator. It's not really doing anything. It's the sorbate that is the thing that's going to affect pH. All right? What is the sorbate going to do to the water? Steal a hydrogen. And it will then turn into C5H7COOH plus, what else does it leave behind? OH. All right, so they're telling me that in this beaker, they've taken 11.25 grams of potassium sorbate and dissolved it in 1.75 liters of solution. So what can you do with that information? Are these units that you put in a rice chart? No, what do you really put in here? Molarity. So guess what you're going to have to do? Calculate the molar mass of this stuff to convert that number of grams to moles, divided by that volume, figure out the molarity of the potassium sorbate that you have in there. All right, so I'll give it to you because I've got the answer key right here in front of me. It's 0.0428 molar. All right? All right, so at time 0, has this stuff reacted with water and made any of these products? No. So this is your I line right here. What do you do with the C line? Lose X, gain X, gain X. What's your E line look like? 0.0428 minus X, X, and X. What's the mass action expression here? X squared over 0.0428 minus X is equal to, what is it equal to, Ka or Kb? Look at what you're making, Kb. They didn't give me the Kb, they gave me the Ka. The Ka was 1.7 times 10 to the negative fifth. All right, so X squared over 0.0428 minus X is going to basically be equal to 1 times 10 to the negative 14th over 1.7 times 10 to the negative fifth. Let me scooch it up so you can see. All right. When I solve for X, the answer that they get is 5.02 times 10 to the negative 6. What does X represent? Look at your rice chart. It's your concentration of hydroxide. All right. So what can you do with concentration of hydroxide? This is your hydroxide. So now you can get the POH. The POH is going to be the negative log of 5.02 times 10 to the negative 6. All right? How do I get the pH finally? It's 14 minus the POH. All right? Are we good? All right, so that's how you do those things. So again, over the weekend, work on Unit 3 for Appendix X. I want it Monday. You're turning it in. I want it this period, not another period. I want it Monday, not Tuesday. Not Wednesday, Thursday, or Friday, and certainly not after the AP exam. Okay? Do page, and this is a little confusing. You have one question on page 157, which is back in Chapter 3, and then the rest of the questions are back in Chapter 6, it's either 16 or 17. All right? And then attempt the POGIL. I want to see at least 3/4 of that POGIL done or more. The more you get done, the better we are on Monday. All right? And by the way, Monday, closed-toe shoes. All right? Good.